In this lecture, we're going to focus specifically on using the quadratic equation to solve for equilibrium concentrations. Once we've seen how to work problems with this approach, we'll talk about simplifying assumptions we can make and when they are valid to use. If you haven't printed these lecture notes out, be prepared to pause often during this lecture. All right, let's work through this example problem. We need to calculate the initial concentrations of the reactants in units of molarity so that we can fill in our ice table. Gathering the information described in the problem, we see that the initial concentration of nitrogen will be 0.500 moles divided by 2 liters, the total volume of the tank. The oxygen concentration will be 0.860 moles divided by 2 liters, and the NO concentration is not mentioned, so it's safe to assume the molarity is 0. This fills in the first official line of the ice table. Entries must be in molarity for the ice table calculations to work. Next, we need to fill in the change line of the ice table. We see that our balanced chemical equation tells us we're going to consume X moles of nitrogen, consume X moles of oxygen, and produce 2X moles of nitrogen monoxide during the reaction. Next, we need to write in the equilibrium values for nitrogen, oxygen, and nitrogen monoxide and drop them into our K sub C expression. We see that K sub C is equal to the concentration of nitrogen monoxide squared over the product of the nitrogen and oxygen concentrations. Trading out concentrations for our equilibrium expressions, we get this equation that we have to simplify in order to solve for X. Let's move that equation to a clean page. The black equation contains the data from the ice table. To get to the next step, listed here in blue, we have to FOIL out the terms in the denominator. First, outer, inner, last. Then we collect like terms, those terms that are raised to the same power of X. This gives us the green equation. Next, we need to clear the denominator, which we can do by multiplying both sides by the denominator to get the purple equation. Finally, we have to distribute 4.10 times 10 to the negative fourth to get the final red equation here. Mathematically, this got ugly pretty fast, so let's take a minute to think through how we can solve for X. Once we rewrite our equation in standard form, we can use the quadratic formula to solve for the 2 roots of X. Standard form means that the terms are written in decreasing powers of X, set equal to 0, and the leading coefficient, A, is positive. If you have trouble recalling the quadratic formula, I found this mnemonic to help you remember it. Now, a word of caution. Only use graphing calculators or web-based calculators to check your work. You must be able to do these calculations using only a basic calculator on the homework and on the exam. Okay, so let's get back to our equilibrium problem. I've repeated our red equation from the previous slide here, as well as the standard form for a quadratic equation in the box. Next, I flipped the equation to get the 4x squared term on the left-hand side. Finally, I rewrote the equation in standard form with all of the terms collected on the left, written in descending powers of X, and set equal to 0. Here's the quadratic equation put into practice. First, I dropped the values of A, B, and C into the equation. Then I multiplied everything out. At this point, I noticed I could make a quick simplification here because 7.77 times 10 to the negative 8th is so much less than 7.05 times 10 to the negative 4th that the 10 to the negative 8th term would get lost in the significant figure rounding anyway. Crossing out this smaller term, we quickly arrive at the simplified equation, which I've recopied to the next slide. Continuing to simplify, we take the square root of 7.05 times 10 to the negative second. Then we need to separate the values of X into the plus and minus expressions so that we can solve for the 2 roots or 2 possible values of X. Once we do this, we have to decide which root makes sense. If you get a negative value for x, that's definitely not the right answer because negative concentrations do not make sense. For the same reason, if you plug a value of x back into the ice table and it results in a negative concentration, that answer also does not make sense. For these reasons, 3.29 times 10 to the negative third is the appropriate value of x. Now that we have the value of x, it's time to solve for the actual equilibrium concentrations. To do this, I've turned our ice table into an IC table with an extra equilibrium line. Here are our final answers. Make sure you have these handy for our next lecture because we're going to make a simplifying assumption about this equilibrium problem and compare the answers from that process to these answers.